Hello everyone, welcome back to Regents Chemistry Review. In this video, we're going to talk about phases of matter. So the first thing that we need to know in terms of the phases of matter is the intermolecular forces. So intermolecular forces are the attractions between the molecules. What we have talked about before is the attraction within the molecule. So for example, if you're looking at the HCl molecule, the attraction between hydrogen and chlorine, so those are called the bonds. But now we're going to talk about if you have two different molecules of HCl, how are they going to attract each other? So the three types of intermolecular forces that you need to know of are, number one, linear dispersion forces, or the van der Waals forces. So these are the attractive forces that occur between non-polar molecules, and they're normally caused by the motion of electrons. These are the weakest type of intermolecular forces. Then we have the dipole-dipole forces. These are the attractive forces between the opposite dipoles of two polar molecules. So for example, if we are looking at two HCl molecules, the partial negative side of the chlorine on one molecule is going to attract the partial positive hydrogen on the other molecule. So that is your dipole-dipole attraction. And then we also have the hydrogen bonding, which also occurs in polar molecules. However, this one is very specific, and this only occurs in the polar molecules that have a bond between hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen. So remember the fun with FON, where we said that hydrogen bonding is only for fluorine, oxygen, and nitrogen. So here's an example of that. So let's say we have two water molecules. So because water molecules have a bond between oxygen and hydrogen, so the attraction between the partial negative oxygen of one water molecule and the partial positive hydrogen of the other water molecule is going to be hydrogen bonding. Please keep in mind that even though it uses the word bonding, it's not necessarily a bond, because bond is only bond is within the same molecule, but in this case we are looking at the attraction between two different molecules. So the reason why we are using the word bond is because hydrogen bonding is the strongest out of all types of attractive forces, or out of these three attractive forces, we should say. So your London dispersion forces are the weakest, dipole-dipole are stronger than London dispersion, and then hydrogen bonding is the strongest out of the three. Okay, so let's talk about the intermolecular forces and how they impact the properties of the compounds. So first of all, let's talk about the phases of matter. We can use table S if you want to determine the phase of any substance at a specific temperature. So let's say I'm asking you to find the phase of mercury at room temperature, which is 298 Kelvin. You're going to go to table S and you're going to look at the melting and boiling points of mercury. And if your given temperature, which in this case is 298 Kelvin, if it's less than the melting point, that means at this temperature, mercury is a solid, meaning it has not started melting yet. If our given temperature is between the melting and boiling point, that means this thing has already melted, but it has not boiled yet. So that means it's currently in the liquid phase. And if our given temperature is greater than both the melting and the boiling point, that means this thing has melted and it has also boiled. So now it's in the gas phase. So liquid, as mercury, as we know, at the room temperature is liquid. Now the problem with this situation is that we cannot use table S for compounds, because table S only gives us the melting and boiling point of elements, not the compounds. So in case of compounds, we can go ahead and compare the intermolecular forces. So remember that if something is in the if something has very, very strong intermolecular forces, that means it's in the solid phase. And if something has weak intermolecular forces, then it's a gas. So for example, if you're comparing two substances, one of them has hydrogen bonding, the other one has London dispersion forces. The one that has hydrogen bonding is more likely to be in the solid phase, and the one that has London dispersion forces is more likely to be in the gas phase or the liquid phase. All right, and then we can also use intermolecular forces to give us some indication about the boiling point, which is the temperature at which a substance starts boiling. So remember that the stronger the intermolecular forces are, the higher the boiling point is. So that's because when we have stronger intermolecular forces, that means particles are very strongly attracted to each other. So they're going to take a longer time to be separated and to convert to a different phase. So that's why they're going to take a longer time to boil. Finally, gram formula mass is also related to the intermolecular forces. So if you have very, very strong intermolecular forces, that gives an indication that this thing is also going to have a higher gram formula mass. Or vice versa, like if you're given the gram formula mass, which is very high, then you can predict that this thing is most likely going to have stronger intermolecular forces. So let's talk about vapor pressure and also like how they are related to intermolecular forces. So first of all, your vapor pressure, let's talk about gases and some of the things that we know about gases. So remember that gases have no definite shape or volume. They have particles that are moving very, very fast. That means they have very high kinetic energy. So remember, kinetic energy is the energy of movement. And because of that, we say that they also have very high temperature. So temperature is also defined as average kinetic energy. If we have very high temperature, that means particles are moving very fast. So meaning they have very high kinetic energy. So let's talk about some of the phase changes that gases can have. So if we convert a solid to a gas, that is sublimation. We go from gas to solid, that is deposition. If you go from liquid to gas, that is evaporation. If you go from gas to liquid, that is your condensation. So let's focus on evaporation for a little bit. If you have water vapors, which is what we get after water evaporates, that is a gas, right? And water vapors takes up more space than an equal mass of liquid water. And that's because in liquid water, your particles are more close to each other compared to the water vapors, because now the particles are very spaced out. So because there's a lot of space between the particles, they are also going to move faster compared to the particles in the liquid phase. So as a result, if we have the gas in a closed container, the vapors that are formed are going to exert a significant amount of pressure on the sides of the container. And that pressure that the particles are exerting on the sides of the container is what we refer to as the water vapor. Okay, so that's what we refer to as the vapor pressure. So here's kind of like a quick illustration of what that might look like. So you see those gas particles kind of like hitting the walls of the container. They're exerting a lot of pressure on the walls of the container. So that's what we call the vapor pressure. So here is a graph that is given to you in table H in your reference table packet. So this represents the vapor pressure of 4 liquids. Some of the pieces of information that you need to remember from this graph is the graph represents that as temperature increases, the vapor pressure is also increasing, because you see all of these curves going up. So that means as temperature is increasing, vapor pressure is also increasing. The second thing that we want to remember here is that this table is telling you is the normal boiling point of these 4 liquids. So normal boiling point is the temperature at which your vapor pressure is equal to the atmospheric pressure. Okay, so atmospheric pressure is the normal pressure in the atmosphere, and then vapor pressure is the pressure that the vapor is exerting on the liquid. So what is the normal boiling point of water? We all know that it is 100 degrees Celsius, right? So if you look at the graph, at a 101.3 kilopascal, we notice that the temperature of water is 100 degrees Celsius. So this gives us the information that 101.3 kilopascal is the pressure at which all of the liquids have their normal boiling point. So meaning the normal boiling point for propanol in that case is going to be about 60 degrees Celsius, so around this point. The normal boiling point of ethanol is going to be about 80 degrees Celsius, but no, sorry, for propanol it's going to be like 55. For ethanol it's going to be about 80 degrees Celsius, and then for ethanoic acid it's going to be somewhere around 5, 10, 117, 118, around somewhere around those lines. If I ask you for the boiling point of water at 70 kilopascal, then this is where this is the boiling point that we have at 70 kilopascal. So that turns out to be somewhere around 90 degrees Celsius, right? So this is how we read this table. So something to keep in mind about your vapor pressure and the intramolecular forces is that as we are increasing the temperature, we are also increasing the average kinetic energy, meaning particles start moving faster and now they are going further apart from each other. So that means that the intramolecular forces that we have between those particles are now going to start breaking, because particles are moving very, very fast, so they don't have the time to be attracted to each other that much. So it's now going to be easier to convert those particles into the gas. So high vapor pressure means we are now going to have a lower boiling point. Okay, so another definition for vapor pressure normally is how likely it is for a substance to be in the gas phase. And so the higher the vapor pressure is, that means the more likely the substance is to be in the gas phase. So in this case, if we are increasing the temperature, we are kind of increasing the likelihood of that substance to be in the gas phase. That means we are going to have very, very high vapor pressure. Okay, let's talk about something else related to the phases of matter, which is the heat transfer. A very important thing to remember about heat transfer is that it always goes from higher temperature to lower temperature. This one is a very, very easy and straightforward concept, but somehow it shows up a lot on the Regents exam. So because it's such an easy question, we should not get this one wrong. Remember that heat is always going to go from the hotter substance to the colder substance. Okay, so there are two types of reactions that can occur as a result of the heat transfer. We can either have an endothermic reaction. So this is the type of reaction where heat is absorbed by the system from the outside. So meaning it enters into the system. So an example of that is we feel hot in the summer. That is because our body is absorbing the heat from the surrounding, because our surrounding is very, very hot. So the body absorbs the heat from the surrounding, because remember, heat transfers from the hotter substance to the colder substance. So that phenomena of us feeling hot in the summer is an example of an endothermic reaction. So some of the phase changes that are endothermic are when we are going from the solid to the liquid phase, meaning when we are melting something, or when we are evaporating something, going from liquid to gas, or when we are sublimating something, so going from solid to gas. Okay. On the other hand, we have the exothermic reaction. So these are when heat is released by the system, meaning it exits the system. So an example of that is we feel cold in the winter. So that's because everything around us, our surrounding, is cold. So in this case, the heat is releasing our body, because remember, again, it goes from the hotter object to the colder object. So heat releases our body, it goes from the body to the environment or the surrounding. So that's an example of an exothermic reaction. So some phase changes that are examples of exothermic reactions are condensation, meaning when we go from gas to liquid, or when we are freezing something, again, the liquid releases the heat to convert into a solid, and then deposition, when we are going from the gas phase to the solid phase. So let's look at something that we call the heating and the cooling curve. So what will the diagrams of these reactions look like? So we use something called a heating curve to represent an endothermic reaction. The reason why it's called the heating curve, because endo means it's absorbing the heat. So it's heating. So in a heating curve, we start with the solid phase, and then we have the liquid phase there, and then we go to the gas phase. So the straight lines that you see, those represent the phase changes, and then the temperature at a specific phase change represents either your melting point or boiling point, depending on which phase is converting into which phase. So in this case, this first temperature that you see is we are going from solid phase to the liquid phase, so that represents your melting point. Then we have the second phase change at the top there, so now we are going from the liquid phase to the gas phase, so that represents the boiling point. So some things to remember about these is that your slopes represent the phases and then the straight lines represent the phase changes. Let's look at the cooling curve as well. So now we start with the gas phase, and then we go to the liquid phase, and then to the solid phase. The straight lines once again are the phase changes. So the first phase change is right there when we go from the gas phase to the liquid phase. So this temperature is going to represent the condensation point or the boiling point. The reason why it represents the boiling point as well is because this is at the same point as your boiling point. So this is the trick that a lot of students miss on the Regents exam, because sometimes they might think that we only talked about the boiling point in the heating curve, but the question gives you the cooling curve and it asks for the boiling point. So remember that it's still at the same spot, because they are kind of the mirror images of each other, the heating and the cooling curve. Alright, so this next phase change then, when you're going from the liquid phase to the solid phase, that can represent either the freezing point or the melting point. Okay, so as we said earlier, phases represent the slopes. Now in your heating curve, at the slope, we see that the temperature is increasing, meaning the kinetic energy is also increasing. Your potential energy, however, stays the same. But if you look at the straight lines, which are the phase changes, at that point, the temperature is staying the same, meaning your kinetic energy is staying the same, right? Potential energy, however, in that case, is going to increase. This is a very, very important concept to remember. It does show up on some of the questions. On the cooling curve, however, it's going to be the opposite. So now at the phases, our temperature is going to decrease because this one is the exothermic reaction. So we are releasing heat. So that means kinetic energy also decreases. Potential energy remains the same, but when we have the phase changes, now kinetic energy remains the same and potential energy decreases. Okay, so if we talk about the heat transfer in the reactions, remember that our reaction is exothermic when we are making the bonds, and it's endothermic when we are breaking the bonds, because we need to absorb the energy to break the bonds. So a quick kind of acronym to remember that is BARF. So BARF means break, absorb, release, form. When you're breaking the bonds, we absorb energy, we release energy when we are forming the bonds. So to find the energy that is absorbed or released in a chemical reaction, we have to do some calculations sometimes. And the equations for those calculations are given to us in table T. So let's look at the first equation right here, the Q equals MC delta T. We also say that as Q equals MCAT. So the Q in this case represents the heat energy that is being absorbed or released, and then the M represents the by the way, we measure the Q or the heat energy in joules, The M represents the mass, the C represents the specific heat capacity, which is the amount of heat that we need to raise the temperature of a substance by 1 degree Celsius. And then the specific heat capacity of liquid water, by the way, is given to us. I'll tell you where in a little bit. But it's 4.18 joules per gram degree Celsius. Sometimes it is also given as joules per gram Kelvin instead of degrees Celsius. And then delta T represents the change in temperature. Please remember that it's going to be final temperature minus initial temperature, always. Please do not do initial temperature minus final temperature. Okay? Now, the other two equations that are given in table T are the equations that we use if we do not have a change in temperature. So these represent the phase changes, because think back about your heating and cooling curves. Whenever the phase change was occurring, there was no change in temperature. So that means for those scenarios, we cannot use the Q equals MCAT equation. So in that case, we use the other two equations, the Q equals MHF or Q equals MHV. Because for these two equations, we do not need the change in temperature. So let's define them. The heat of fusion is the amount of heat that is required to freeze or melt 1 gram of a substance, and the heat of vaporization is the amount of heat that is required to vaporize or condense 1 gram of a substance. We are given the heat of fusion, heat of vaporization, and specific heat capacity of liquid water in table B. So most of the questions that you're going to get about heat of fusion and vaporization are going to be about liquid water. So you can just get the heat of fusion and heat of vaporization from table B. If the question gives you, or if the question asks you to do the calculation about something other than liquid water, then you will be given the numbers. So the very, very important thing to remember here is after you do this calculation, you look at your answer to figure out whether your reaction was exothermic or endothermic. And how do we do that? If the Q, or the heat energy that you have calculated, is negative, then that means your reaction is exothermic. And if your calculated Q is positive, that means the reaction is endothermic. Okay? So let's look at some examples of the heat calculations to make sure that we are all okay with the heat calculation problems. So here they're asking us to calculate the amount of heat required to raise the temperature of 15 grams of water from 20 degrees Celsius to 50 degrees Celsius. So because you see a change in temperature, that tells you that we can use the Q equals MCAT equation, right? So we are given the mass of water. So this is the mass of water for your delta T. We're going to go ahead and convert these degrees Celsius into Kelvin first, because our specific heat capacity in table B is given in degrees Celsius. So it's given in Kelvin, not degrees Celsius. So 20 degrees Celsius, if you want to convert this to Kelvin, we do 20 plus 273. That gives us 293 Kelvin. And then 50 degrees Celsius will be 50 plus 273. So that is going to give us 323 Kelvin. Okay, so then your delta T is going to be, remember, final temperature minus initial temperature. So that will be 323 minus 293, and that will be about 30 Kelvin. Okay, so then we go ahead and plug everything in the equation. Q equals MC delta T. So your mass in this case is 15 grams. We are looking at liquid water. So remember, the specific heat capacity of liquid water is given in table table B, that is 4.18 joules per gram Kelvin. And then we have the delta T, which is 30 Kelvin. So just do your math, multiply all of these things, and we get about 18,998 joules. Now, sometimes if you have a bigger number like this, it's okay to leave it like that, but sometimes they might also ask you to convert your answer into kilojoules. So if I ask you to give me your answer in kilojoules, remember kilo means 10 to the power of 3, which is 1,000. So that means we are just going to go ahead and divide this by 1,000, and that gives me 18.998 kilojoules. Okay, so what if I give you a question like this, where we have 20 joules of heat added to 2 grams of water at 15 degrees Celsius. The temperature of the water increases too. So in this case, I already gave you the Q, or the amount of heat energy. And then we have the mass of water. We also have the initial temperature, the TI. Let's go ahead and convert this to Kelvin. So that's going to be 15 plus 273. So that is about 288 Kelvin. So we are looking for the final temperature. So TF is unknown. Let's go ahead and write the equation. Q equals MCAT. Instead of writing delta T, I'm going to write TF minus TI. So we're going to open up the equation. And that's because we want to isolate the final temperature from this equation. So the first thing that we can get rid of is the MC. So let's go ahead and divide MC on both sides. After we do that, we can cancel MC over here. The next thing that we want to isolate is the TI. So we can go ahead and add TI on both sides. So TI, remember, is your initial temperature. So we can get rid of the TI on this side. So now our equation becomes final temperature equals Q over MC plus the initial temperature. So if I go ahead and plug in all of the numbers, we have 20 joules divided by your 2 grams times the specific heat capacity of water, which is 4.18 joules per gram Kelvin. And then we are going to add the 288 Kelvin to this. And that gives us about 290 Kelvin. So this is your final temperature. Okay, so let's look at some more heat calculations. This one is asking how much heat energy is absorbed when 10 grams of ice melts to form liquid water at the same temperature. So we are talking about the melting of ice. So that means we don't have a difference in temperature. So we cannot use Q equals MCAT. And because the phase change here is melting, so the equation that we are going to use is the one with heat of fusion. So Q equals MHF. So the mass that is given in the question is 10 grams. We are talking about liquid water. So the heat of fusion for liquid water is already given in table B. So that is 334 joules per gram. So once we multiply both things, we get 3,340 joules. Here's the last question to practice. How much heat is absorbed when 70 grams of water is completely vaporized at its boiling point? Once again, no change in temperature. So we cannot use Q equals MCAT, and we are vaporizing something. So that means the equation that we are going to use here is Q equals mHv. This is for water again, so the mass is 70.0 grams, and we get the heat of vaporization for water from table B, so that is 2260 joules per gram. So when we multiply both things, we get 158,200 joules. So once again, because this is a very long number, let's practice converting this to kilojoules. You can go ahead and divide this by 1,000, and we get about 158.2 kilojoules. Alrighty. Finally, let's talk about the last concept about heat, and that is calorimetry. So calorimetry is the science of determining the change in the heat energy, meaning is the heat energy absorbed by the system or is it released by the system? And we do that by measuring how much heat, once again, is absorbed or released. So this is kind of what the setup of the calorimetry looks like. So we normally have like a styrofoam cup. We have a substance, which is a system which is surrounded by something, and then we use a temperature to measure the difference in temperature. We have a thermometer to measure the difference in temperature, and that we just plug in the numbers in the Q equals MCAT equation. And that kind of helps us determine if the system absorbed heat or released heat. So remember that in this case, let's say this is the metal that we are using. So the metal is going to be the system, and then our water is going to be the surrounding. So we are trying to determine if the system is absorbing heat from the water or is it releasing heat from to the water. So the thing to remember here is that heat transfers from high temperature to low temperature always. So whichever substance is hotter, heat is going to go from that substance to the colder substance. And according to the law of conservation of energy, if we are using, let's say, a hot metal, then the heat that is going to be released by the metal is going to be equal to the heat that is absorbed by water. And as I mentioned earlier, the equation that we use to calculate the heat absorbed or released is Q equals MCAT. If the Q turns out to be a negative number, that means we have an exothermic reaction going on for the system. And if the Q turns out to be positive, that means we have endothermic reaction going on. Alrighty, so that was the end of the physics of matter. I'll see you on the next one.